Hi, everyone. I'm Eric Brynjolfsson, and this is the Digital Economy Lab lunch seminar. We're delighted to have this week Daniela Rus. Daniela runs the CSAIL, the AI, Computer Science and AI Lab over at MIT, where I was for so many years. And it's always good to see Daniela again. We've been friends for decades. She's a MacArthur Fellow, a Fellow of the ACM, AAAI, IEEE, National Academy of Engineering, Academy of Arts and Science. I'm going to stop there because I would spend the whole rest of the day reading the rest of her accolades. She has a lot of interest in robotics, mobile computing, data science. She has a couple of new books. She was busy during the pandemic. One is called The Heart and the Chip, Our Bright Future with Robots. And the other one that she was just telling me about is The Mind's Mirror, Risk and Reward in the Age of AI. I guess one came out in March and one in August. So yeah, she's been doing a lot of different things. So we welcome and encourage questions during the seminar the way we usually do it. If it's okay by you, Daniela, if there's sort of a clarification question about something on your chart during it, but then more broader questions, we save most of those towards the end. I'll be monitoring online, so if you have questions online, you can just put them into the Q&A there, and we'll bring up a few of those. And if you're in the room, just raise your hand, and we have microphones, and we'll bring them over there. So with that, welcome, Daniela.
Thank you. I'm really so delighted to be here and to tell you a little bit about what we've been up to in this grand age of AI. It's such a special moment for our field. And so today I will explore with you a bit how we integrate advances in hardware with artificial intelligence and how these advances enable machines, whether they are robots or satellites or power grids, how they enable these machines to become more intelligent. And so physical intelligence or physical AI is really the idea of increasing the brain capacities of machines by using AI technologies that are able to understand text, images, and other online information to improve the capabilities of machines. And so now this means that AI can help pre-programmed machines do their tasks better. And this is different from embodied intelligence, which is about using the hardware, the body of the machine, to make intelligent and adaptive decisions about interacting with the environment. So let's see. Now, let me start by observing that today in the field of computer science, we have two largely separate fields. We have artificial intelligence and robotics. And AI is amazing us with its decision-making and learning, but it is confined inside computers. Now, robots have a physical presence and the ability to execute pre-programmed tasks, but they are by large not intelligent. And so what I'm interested in is bridging the separation. I would like to see physical AI enable machines and AI that doesn't just reside in the digital world, but I want AI that walks, rolls, flies, and interacts with the world in extraordinary ways. So just imagine being surrounded by robots at the supermarket. This image has 19 robots in it. The one on the left can help you carry a box. Now, in order to make this physical AI work, we really need to change how machines think, how they're designed, and how they learn. And let me tell you why. Now, it is challenging to use today's AI models on safety-critical applications, such as the ones with robots, because these models make mistakes. And so this is an example of the AI output on a robot car. And the robot car is really great at detecting individual pedestrians because it's been trained on a lot of data on what an individual pedestrian looks like. But it has trouble with groups because they are amorphous and maybe the particular geometry of the group has not been seen before. So for physical AI, we really need brains that do not make mistakes. Now, for physical AI, we also need software that can run on the small computers on the body of the machine. For example, this robot fish. But today's AI doesn't fit because it requires server farms. And so additionally, today's AI has a very high energy cost, and this cannot be covered by onboard batteries. And so let me explain a bit this energy cost. So the energy cost is very large because of how frontier models are built. Now, today's frontier models like ChatGPT, Claude, or Gemini are very large models on the order of trillions of parameters, and they're basically built in 2 or 3 energy intensive phases. The first 2 phases are called pre-training and fine-tuning. And the goal of pre-training is to have the model learn from general knowledge that is embedded in the data. And the more knowledge is provided as input, the better the models perform. And so, for instance, you can train the model on between 1 and 15 terabytes of data. And the result of that is that the model learns the weights in a transformer architecture so that the trained model can complete sentences. For example, Stanford was founded in, and you expect that the model can respond 1885. But in order to make that happen, you actually do need a fact about when Stanford was founded in your training data set. Now, the second phase is called fine-tuning, and here we use specialized data to adapt the model to do useful downstream applications, for example, to follow instructions. So you can feed the model all the proceedings from the International Conference on Learning Representations, and you can ask the model to do things like summarize papers or find connections between papers. Now, in addition to pre-training and fine-tuning, many machine learning solutions use another step, namely reinforcement learning, in order to align the behavior of the model with human preferences and real-world goals. And so with reinforcement learning, you optimize the model through reward signals, and these reward signals are often received from human feedback. So this complete pipeline consumes a huge amount of energy. And in fact, AI is projected to use enormous amounts of energy in this decade. As of today, the projected US data center share of the total US power demand is about 5.2%. But this amount is projected to grow, and it's projected to go between 12% and 6.7% by 2028. And so that's an enormous amount of energy that also has a high carbon footprint. And the question is, what can we do about it? Well, we have, as a community, we have developed a number of solutions to simplify the models without using its effectiveness. And one technique is called pruning. And in this technique, we have algorithms that look at the models and decide which parameters in the model are important and which are not important, and then the unimportant parameters are removed. Another technique is called quantization, and quantization reduces the precision of weights so that the computations are faster. So for instance, instead of using 32-bit floating point numbers, quantization allows us to use 8-bit integers. And with these techniques, we have seen tremendous progress in machine learning. And so, for instance, DeepSeek has recently shown that these ideas, along with great engineering, can result in significant energy reduction for the training and pre-training of large frontier AI models. In other words, they have shown that it is possible to get the best model performance with far less cost than it was previously thought. And specifically, what DeepSeek did was to train a 671 billion parameter model using a series of techniques that included quantization, pruning, dropping down to PTX, which is the assembly language that sits just above the NVIDIA GPU. And then with all these techniques and great engineering, they achieved a 45-fold increase in the training efficiency, which is extraordinary. This is also how the cost of operations with DeepSeek went down. So as of today, a single training run costs about $5.6 million, which is an order of magnitude smaller than in previous models. Okay, so we have seen some examples of energy savings. Now we can take these energy savings, we can take these techniques, and we can use them to support more scaling. But as we continue to build larger and larger AI models, we are also beginning to see that the thesis that pure scaling of the next token prediction models will continue to increase the performance of the models. This thesis is beginning to show diminishing returns from the point of view of capability. And here's some data. This data shows how scaling impacts of the model's performance on a challenging benchmark called MMLU are beginning to show diminishing returns. And so this is raising an important question. And the question is, are there new ideas? Are there ideas that do not make mistakes, that result in small models that can fit on machine bodies that will lead to better performance than transformer-based architectures? So we are using inspiration from a humble worm called C. elegans to answer this question. And in stark contrast to the billions of neurons in the human brain, the worm lives happily on only 302 neurons. And biologists understand how these neurons work. And so here's the idea. Can we use the math of the worms to build a new class of AI algorithms? And we call those algorithms liquid networks. Let me show you how liquid networks work. So this is our self-driving car. In this video, the car has been trained using a traditional AI solution, deep learning-based, the type that you see in many AI applications today. And here is the dashboard of the car. So in the lower right corner, you see the map. In the upper left corner, you see the camera input stream. And the big box with blinking lights is the decision-making engine that tells the car how to steer and how to accelerate. Now, this car learned how to steer and how to accelerate by watching how humans drive. Okay. I'd like to call your attention to this video. This is the attention map. It actually represents where in the input stream the decision-making engine looks in order to make decisions. And what do you see? Well, you see that it's very noisy. It's kind of it's very noisy, and the decision-making is focused all over the image, and sometimes on the bushes and the trees on the side of the road. But that's not how humans make decisions when to drive. So I would say that this solution is very focused on the context of the driving task rather than the driving task itself. Now, contrast this with the liquid network solution. Oh, I forgot to tell you. Here we have, in this solution, we have about 100,000 neurons in our liquid network, in our deep network, and we have about 500,000 parameters. And so it's really impossible to correlate how 100,000 neurons fire to what the car does. It's just too complex. Now, contrast this to the liquid solution, which you see here, and look at the attention map. You see how clean it is and how focused it is on the road horizon and the sides of the road at the horizon. This is much more in line with how humans make decisions when humans drive. And the other thing is look at how sparse the solution is. We have 19 neurons instead of 100,000 neurons. And given this small solution, we can now extract decision trees that explain the role of each of these neurons in the ultimate decision of the vehicle for steering and for accelerating. So how is this performance possible? How can we go from tens of thousands of neurons to 19 neurons and get this kind of extraordinary behavior? Well, in a traditional AI solution, the traditional neuron takes in some numbers, adds them up, puts them through a simple computation called the activation function, and puts out a 0 or a 1. And this is complicated because it's happening across many, many computational units. So liquid networks use fewer neurons, but each one does something more complex. And so here's what's happening in the liquid solution. First, we use differential equations, which are inspired by what biologists determine happen in the neurons of worms to represent the computation of the neuron and also the synapse. And when you plug the two equations into each other, the synapse into the differential equation that describes the function of the neuron, you get this thing, you get this hairy equation over here. So it's a kind of a complex differential equation, but I'd like to call your attention to two things. First, in a typical differential equation, the term in front of x of t is usually the time term, and it's usually constant. Here, we don't have a constant time. We have something that depends on x of t. And from a mathematical point of view, this is very exciting because it points to the ability of our solutions to adapt after training. And the other exciting thing about this equation is that it has a closed form approximation with an upper bound. So the closed form approximation is still hairy, but it doesn't require numerical integrators. So that means that computing what this equation should return is very fast. And these changes yield enormous benefits. So in most AI solutions, you actually have static solutions. In other words, if you use a traditional solution, you deploy it on your application, that solution is frozen. If you need a change, you have to wait for the next release. An interesting aspect of liquid networks is that they continue to adapt after training based on the inputs that they see. And they're also very fast and energy efficient. Eric?
I think I see where the X's come from. Where does the T come from? Is that just changing over time as it runs, or how does it know?
So that's a good question, Eric, because that also points to a limitation of liquid networks. In other words, these solutions only work for time series data. So if you have data that comes in sequence, then you can use these solutions. So good point. Okay, so I want to show you an example that highlights adaptation. And so we trained liquid networks and a whole slew of other more traditional solutions for machine learning to find things in the woods. For example, this red chair. And we trained them using unlabeled data, like what you see in this video. And all the solutions learned how to do this task in the summer. So we had a bunch of models, and then it got to be fall in Boston. And so we tried the models that we trained during the summer again. And here's what happens to the standard deep neural network solution. There's a drone, and you can see how confused it is. Look at the attention again. And so the drone doesn't know what to do because the solution actually looks at the entire context of the task. And now the context is very different. The task itself is the same. But instead of summertime, green, leafy background, now we have this other rusty, leafy background. It doesn't work. This is the liquid solution. So the liquid model has no problem focusing on the task and then proceeding to the task. So it turns out that this model, trained in the summer, also works in the winter when there are no leaves on trees. And you can also take it from the woods and put it in an urban setting. And you can also take it from applications that have static objects to applications where the objects move. So this kind of out-of-distribution adaptation is a very exciting property. Part of the reason is that these liquid network solutions are provably causal. That means that they learn how to associate cause and effect, and the other solutions are not. So Eric asked about the time series nature and of these applications. So it turns out that you can use this approach to AI on any application that has time series data. And the data can be anything. The data can also be multimodal. And so we compared the performance of liquid networks against transformers on a number of tasks and data types. For instance, for physical real-world dynamics modeling, we see 123% improvement over transformers. For information retrieval, we see 10% improvement. For text sentiment analysis, another 10% improvement. So you can think of text as time series because words come one after the other. We also had medical applications. So we were very encouraged by these results and decided to bring these results to the world in the form of a company we call Liquid AI. We've been working on this company for about 2 years. And in September, the company released its first liquid foundation models. And we compared these liquid foundation models against existing open source models. And here you see the performance of the models on a challenging benchmark called the MMLU Pro benchmark. And you can see that the liquid models have much higher performance than the existing models. The other interesting aspect of this is that the liquid models were trained on a small number of GPUs, on the order of a few hundred, rather than a few tens of thousands, which is the standard practice for training transformers. The other thing that's really interesting is that the memory footprint of the liquid foundational models is small as compared to transformers. And so here you can see how the memory footprint grows with respect to the number of tokens, with respect to the output length. And this makes the liquid models well suited for small devices like your phones. We can run these models on your phones or on your computers or on the machines that our robots carry. So this is the memory footprint for 3D models. 7D models are quite similar. And these models are also quite performant for translation tasks. And so here you can see how the liquid models compare with other models in English to Japanese translations. And we can see more detail. And so this chart was done by a head-to-head evaluation that shows the proportion of times the liquid foundation model jury preferred the answer generated by the LFMs over the other models. And so this is, yes, Eric?
Yeah, so this is fascinating. And so a lot of the GPUs, TPUs have been optimized for transformers. And the math is pretty different in the liquid networks. But you're running, I guess, on the existing kind of hardware. Is there further room to have chips that are optimized for liquid? Yeah, okay.
Yes. So very exciting. But actually, GPUs have been optimized somewhat, but GPUs were introduced a long time ago, and they were not introduced for AI applications. They were introduced for graphics applications. So I would say that the whole field of AI could stand to benefit a lot from dedicated chips, whether the dedicated chips are are built for transformers or for liquid or for other types of technologies. So anyway, this is very exciting. And observing this great performance on text gave us other ideas. And for instance, the ability of the liquid foundational models to handle multimodal data means that text and other sensor signals can be used together. And this gives us another benefit. This gives us the opportunity to think about control tasks and think about intelligence as not just the connection between perception and action, but as the connection between perception, action, and language. And language is really important in intelligence. For those of you who are familiar with robotics, in robotics, we often spend time thinking about the pixels in an image or the XYZ coordinates we need to manipulate in order to plan. Language is at a different conceptual level. Language provides us with abstractions that essentially elevate the level of reasoning from pixels and XYZ coordinates to concepts. And so we were very excited about the possibility of exploring this. And here is an example. So let's say we have this image and some text describing it, which could be extracted in an autonomous way. It turns out we can build a foundational model that aligns the perceptual features and the language features in the same latent space. And then it turns out we can train a model to control relative to some concepts, for example, to avoid a deer, using video data for how to avoid the deer, how to steer the car to avoid the deer. And once you've learned how to do that, you can then use language. You can use concepts to say, now also avoid people and trees and buildings and benches and anything you come up with. And this actually really expands the ability of our models to adapt to out-of-distribution scenarios in a way that is very energy efficient, in a way that does not require lots and lots of videos of cars avoiding trees and cars avoiding benches and cars avoiding buildings. I need a camera in my back. All right, so here's how this works in practice. Okay, so first we find a set of textual features that are relevant to the task, in our case, driving. You can use any task you want. Then we curate a set of features to be swapped in as simulation targets. And finally, we simulate the image features by sensibly swapping in with the target features. And the end result is that we can train a vehicle using video data in one scenario, and then we get direct generalization to a diverse set of out-of-distribution scenarios. And this is in a closed loop setting. So for instance, we can avoid animals, and we can avoid cars, we can drive in the winter, we can drive in the fall, we can drive at night. What else have I got here? We can drive with perceptual challenges like the sun impacting the camera. And we have some quantitative results where we're looking at how many crashes do you get in simulation if we use our method versus not. And you can see that our method results in 0 crashes, whereas all the other methods have many crashes. So this is super exciting because now we have the possibility of using AI on device, and we can use it in an energy efficient way and also in an adaptive way that is amenable to these kinds of extraordinary generalizations. So what else? Well, I told you that we needed energy efficient AI that runs on device, but we also needed to find some ways to avoid the mistakes. And so let me tell you a little bit about how we think about that. Now, the question is, how do we ensure that there are no mistakes? For example, in driving, no crashes. Well, it turns out that the control theoretic community has spent a lot of time developing mathematical machinery called control barrier functions. A control barrier function essentially is a mathematical expression that defines the region of safety for an application, whatever the control application is. And so our idea was to ask, can we use control barrier functions with machine learning? In other words, can we take a machine learning model and wrap it with another layer that effectively implements a control barrier function that effectively pushes the output of your machine learning model, your AI model, into a safe region? And that's exactly what we did. We call this barrier net. And barrier net is a little bit mathematically hairy. You can kind of see how we do this. So for what we have to do on an application by application basis is to define the control barrier function, to define the mass of what is safe. And you can do this for driving. You can do this for a wide range of other applications. For instance, you can define toxic speech in terms of mathematics, and you can add a layer that defines toxic speech. You can look at generating new chemical compounds. You can define what is dangerous in the process of generating chemical compounds. So for every application, you could take a mathematical formulation of what is safe, you add it as another layer of your machine learning AI solution, and you get a barrier net where you have the guarantee, provably, that the output of that model will be within the safe region. You still don't know how the system arrived at that answer, but you do know with guarantees that the answer is safe. And this is very exciting. And so in robotics, we have taken this idea and applied it to a range of applications. So here you can see some challenging driving tests, especially in the case of very strong sunlight that provides challenges for the perceptual system of the car. We also applied barrier net to this flying task. So this was inspired by the movie Maverick. If you've seen it, if you're not, you should probably see it. So here the idea is you have a plane. It's flying in a canyon. It cannot crash into the canyon, but it also has to hit some targets. And so you can see the control of this vehicle with barrier net. The vehicle crashes very fast in the absence of barrier net. And the liquid network solution for this has 22 neurons, which is really quite extraordinary. So here is another one where we're playing with boats, with autonomous boats, and we're getting the boats to navigate through a water canyon. We also applied it to robot swarms. And so here you see barrier net controlling a group of robots and preventing them from crashing into each other as they explore an environment. And in this environment, they have to go through narrow openings. And here is a physical realization of a swarm where the robots, again, cannot crash in each other, but they have to cooperate in order to push a heavy object, an object that's too heavy for a single robot to push. So I hope I convinced you that the future is bright from the point of view of physical AI. We can develop new technologies for AI that are physics-based, that result in compact solutions that are understandable and explainable, and with barrier net that can be made safe, and that can run in an energy efficient way on bodies of physical machines. Now, at the beginning of the talk, I said that we needed to do three things to enable physical AI. The second aspect is designing AI solutions. And so we can use AI to define how the machines we want to use really look like. But we cannot do that using today's AI solutions because they do make mistakes. They use statistics. They do not understand physics. And so I'm sure that by now all of you have generated images using your favorite chatbot. And so I was interested in a new research robot concept a soft robot that could pick delicate fruit off of trees. And so I posed this query, and this is what happened. Now, I have to say that these are very wild and cool and creative ideas. I love them. But let's see how good they are in the physical world. This is my favorite example. And so if you look a little bit more closely, you can see that, first of all, the stem is so tiny. So it seems to, like, how are you even going to lift something with that tiny stem? And it seems to define physics. And then we have this manipulator where both ends seem to be fixed. So how is that going to manipulate anything? And finally, how do you even fabricate these kinds of surfaces? It's very challenging. So it's very cool, but it's not practical. Well, in our lab, we actually developed an alternative to these design tools that can actually generate physical designs that meet physical requirements. And so, for instance, you start with a language query, for instance, design a robot that can walk forward. And our system generates the design, including the shape, the materials needed for the design, the actuators, the sensors, the fabrication files to 3D print the design, and also the low-level control software to control the design. And using a physics simulator, the designs generated by our system get refined and they get checked against the physics simulator. So this is a snapshot from the simulation process. You have a blob, and after some more time, you get this design that is sort of weird. It looks like a table with worms as legs, and maybe you can even get a walking teapot at some point. So the question is, how do we do this, right? I mean, how do we do this? Oh, I have one more example. Here is, you can see a gripper that we generated in this way. So here's how it works. We train a diffusion process to map 3D shapes to noise and their corresponding embeddings. And then the diffusion process, which is in green, guides the sampling process with co-designed gradients from differentiable simulation by reformulating the diffusion sampling process into a joint design and control optimization. And then we the embedding process optimization in blue iteratively generates new robot designs to evaluate for training and conditional embedding. And once we settle on a design, we have to convert it and we have to, in some sense, convert it into a physically simulated machine. And we do so. And then we evaluate it in simulation. And we get the output of the simulation engine and feed it back into the design process until we reach a certain level of optimization. So basically, it's a diffusion process that uses simulation as a way of capturing the physics of the world and the task requirements. And here you can see some of the designs, and so you can see some of the tasks we have done. We have hurdling, box moving, grasping, passive dynamic landing. Anyway, you can take your favorite physical task and stick it into the simulator, and you will get a design. And so this is really exciting because now it means that we can generate anything from text. And we can generate physical things that understand the laws of physics and that also can incorporate task requirements. Now, the other thing we can do is we can also do image to robot. So you can think of that as text to robot. Now we can do image to robot. And this photo can be transformed into a cuddly robotic bunny. This is the stand for bunny, by the way. So to do that, our cutting-edge algorithm computes a 3D representation of the bunny. Then it slices it into layers that get unfolded and printed. Then we fold the printed layers. We string some motors and sensors. We write some code. And we get the bunny in this photo, in this video. Now, this approach can be used to make almost anything from a photo. So using AI to do text to robot and image to robot is incredibly exciting because it means we can greatly accelerate the innovation cycle. We can introduce efficiencies that are just not possible when manufacturing is a manual process. And if we do this, we can prototype new products, we can test new products. Basically, we allow a much faster innovation cycle. Okay, so now we know how to make machines. We know how to get these machines to think, and we are ready to think about the complete leap to physical intelligence. Basically, we can get the machines to learn. And the interesting thing is that we can get these machines to learn from humans how to do tasks. So you can think of this as human to robot. And so in our lab, we created a kitchen environment where we instrumented people with sensors and collected a lot of data. We recorded pose, muscle, even gaze when people perform everyday kitchen tasks. And this is actually very important if we're trying to learn how to manipulate the environment, because the forces and torques are not immediately readily available by watching videos. Also, a lot of these tasks are too complicated for modeling them mathematically from first principles. So we don't really have many options for getting machines to replicate them. So anyway, we collect all this data, and then we use AI to learn from this data how to get robots to perform these tasks. And so the end result is machines that move with delicacy, machines that move with grace, machines that move in a more human-like way than in this kind of mechanistic, robotic-y way, which is what you see when people program robots from scratch. And so we're very excited about this. We can apply this method to teach robots how to do food preparation, cleaning, and more, using data from how humans do these tasks. So the ability to turn photos and words into functional machines, coupled with the ability to use liquid networks to create powerful brains for these machines, is incredibly exciting because it means you can build almost anything you imagine. Now, I believe that many of today's AI methods have a ceiling. They have a high energy cost. They have hallucinations and mistakes. When we move the AI ideas into the physical world using new technologies that some exist, some have yet to be invented, maybe by some of you. When we bring AI into the physical world, we will see extraordinary benefits. We will see personal assistants that optimize our routines and anticipate our needs. We will see bespoke machines that help us at work. We will see robots that delight us in our spare time. The promise of physical intelligence is to transcend the human limitations with abilities that grant us the ability to extend our reach, refine our precision, and amplify our strength, and give us opportunities to interact with the physical world in ways that we have only imagined. But as we move forward with our ideas about physical intelligence, we really have to do so with a guiding hand, because we remain responsible for everything we do, for our planet and for everything that lives on it. And so for me, studying physical intelligence is teaching me that there's so much more left to learn about AI and also about ourselves and about how we use these extraordinary tools in the world. And there are many questions that we need to answer sooner rather than later before this technology plays out without a guiding hand. Thank you very much.
we have some time for questions right over here.
That was super fascinating. Thank you so much. I'm wondering, so this method really makes it plausible that machines can learn on themselves using limited computing power. And I'm wondering how you think about aggregating what they learn. Because if we think about humanity, arguably what makes us really distinct as a species is that our collective intelligence really allows us to do things that animals can't do. So I wonder, once a machine has learned something new about the world, how do we aggregate all of that knowledge to more centralized intelligence?
So it is possible to aggregate the models that AI learns, and there is a big community that's working on this problem. One of the techniques that seems to be most promising is called transfer learning. And so the idea then is, how do you learn something in a more generic way? And here, the technical details are actually very important, because let's say you have trained a robot car to drive on the road. How can you take that model and map it onto a small robot that delivers food, or that delivers your produce that you picked up at the supermarket? The transfer is not so straightforward, because the dynamics of the first task is quite different from the dynamics of the second task. This means we really need to aspire to develop more techniques that are provably causal. In other words, that learn the essence of the task rather than the context of the task. And right now, most of the AI techniques that are in use are not causal, are really focused on context rather than the task itself. And so, to accelerate transfer learning, we need more provably causal solutions for AI.
Yeah, very nice talk. In the middle, you had a couple of examples about physics and how the algorithm was following the rules of physics. How did you teach it physics? I mean, it was doing things in three dimensions, and it was yeah.
So I didn't teach physics. I used a different technology that somehow has physics embedded in it. So the transformer model has a very simple computation. You can think of it as a step function. But there are other ideas for how to build the computation of the neuron that is physics inspired. And so the differential equations that were inspired by the humble worm are a different technology, are physics inspired. I'm not sure which problems you or which examples you asked about. I would say that for in the fruit case, yeah. So that's a different story. So in the fruit case, the physics comes from the simulation. So I don't explicitly build the physics in the model, but I take what the model gives me, and the model is essentially a diffusion-based model. I take the output of that model and I simulate it, and I see whether the physics is correct or not. And if it's not correct, I throw it out and I send a signal back into the generation engine, and I try again until the physics is captured. Yes.
So for autonomous driving, the liquid network achieved like 1,000 order of magnitude difference in the number of neurons. However, for LLM or foundation models, I see the number of parameters are on the similar side with other models, not the order of magnitude. Can you explain why?
Yes. So building a foundational model in the liquid framework is the same as building a foundational model in other frameworks, like in transformers, like with transformers, for instance. But what we get is better capability. So we have increased representation capability using our models. And so if let's say I disconnected So I can build a model that's as big as I want. My 3B model will do more than some other 3D model that is based on the transformer architecture. So so that's one advantage. The other advantage is that all of my computations will be much more energy efficient. I mean, ultimately, with these models know what you train them to know. So if you don't give them much information, then they won't know so much. So the more information you give them, the better the models are, which is why it's kind of advantageous to build big language models. But the point is that you don't need to build the really huge models in order to have good performance.
What are the differences in the types of features that are found in liquid neural networks versus traditional transformer-based networks?
How do you mean that?
I guess like if you were to use like a sparse autoencoder to isolate a layer and try to derive like
So the layers are the layers in the liquid technology are quite different from the layers in transformers. In fact, I didn't tell you this, but we do wire the neurons differently, and we wire the neurons differently in order to allow for recurrences. And this is a very important advantage that the liquid technology has. If you read the transformer paper, the third or fourth sentence in the paper says we do away with recurrences and convolutions in order to increase parallelism and efficiency. And so the transformer is a feed-forward model. The transformer does not look back. Well, we thought that there was some advantage to looking back because feedback is a very important aspect of intelligence. And so what's different from in the liquid model is the loops. It's the ability to have recurrences, the ability to learn from past experience.
Thanks for the talk. I have a question on the control barrier function part. I saw the barrier net where you can also write down the differential equations. And is the solution, the analytical solution, a precise one, or that's a approximated one?
Yeah, you have a closed form solution.
Yeah. So that's precisely solve that differential equation.
Well, okay. So sorry. Let me back up. The equations are task specific.
Right.
And so how you solve them is it depends on
the form. Yeah. Okay. So so does that lead to a significant amount of efficiency improvement comparing to the current AI approaches?
Well, it leads to safety. Okay. And it also leads to solutions that are safe but not as conservative as the solutions that you might develop from scratch.
Right.
From first principles.
I see.
So, I mean, if you're less conservative, then that means you're more efficient.
Yeah. Right. Thank you.
I had a question about that. So you were showing, like in the kitchen, learning they had some haptics, some feedback, but there's also videos. There's a lot more video data than there is people being recording, when they're picking up an egg, how much force they use. Where are we in terms of being able to have the systems learn from just video and maybe audio, the stuff we have a lot of, as opposed to having to instrument to get a lot of data?
So, and that's a great question. The challenge with video is that it really doesn't capture the physical interactions. It doesn't, I don't know, if I just watch a video, I don't know what the friction coefficient is. I don't know how much force I have to apply in order to pick this up. And so if you don't actually have real feedback about the dynamics of the task, it's just really difficult to get that from the video. You can get kinematics from the video,
was wondering, to connect it to another point you made, was where you're using language. Like you'd say, okay, this person is picking up an egg versus this person is picking up a cue ball. It may be look the same, but we know, that you have to be more careful with eggs. Is there any potential for having some of those like higher level concepts feed through to the kinds of forces that are used?
Yeah, Eric, there is. Maybe you should come back to MIT and work with us on that. So yes, so there is some potential, but to be honest, I don't know exactly what amount of dynamics is needed and what amount of kinematics is needed. A lot of people are trying to learn tasks from watching videos, and many essentially try to attach simulations to what they learn from extracting information from videos, and use simulation as a way of trying to figure out the dynamics, and that's a very exhaustive process. So I think that I need to put some. I think I need to apply some force in order to pick this up. I'm just going to exhaustively try pushing harder and harder and harder until I manage to do it in simulation without breaking it. So there are methods that people are trying. I just find this notion of preparing the dynamics side as part of the core learning process much more likely to get us to the goal fast.
Let me ask a sort of a follow-up, going in the opposite direction. You've also done a lot of work with self-driving cars and other things. Some of them use LiDAR and other senses, or just in general, there are a whole lot of things in the electromagnetic spectrum and everything that humans don't have those senses, but we could give them to robots.
Yep.
And so, what are your thoughts on whether, on using those other dimensions? Elon Musk said we shouldn't try to use LiDAR because humans don't need it. Others, like I was just riding the Waymo car yesterday, and obviously they do use it. Do you have any thoughts about using these extrasensory senses?
Yeah. So look, I just want to say that everything I talked about is multimodal. It's not just vision-based. The techniques also work with LiDAR. In fact, I think LiDAR is a very important sensor for safety-critical applications, primarily because image-based reasoning is not 100% reliable. LiDAR gives you very accurate measurements. And so with LiDAR, you really know that there is an obstacle in front of you. You don't have the problem of, the machine learning system mistook the cluster of passengers for cloud or something like that.
But there's a whole set of stuff. I mean, so
sure.
Roddy Brooks, his Baxter robots have the ultrasonic. I can imagine others. Are there ones that you think roboticists should be thinking more about using or are using that, or the other dimension is being very humanoid and saying, okay, let's kind of match our senses.
So let's see. So we have colleagues who are building smell sensors, and they're really, really interesting because I've just seen this talk that blew me away. With a little sensor that you get stuck in your nose, you can actually get tricked into thinking that you eat delicious ice cream, and in fact, you eat broccoli. So it's really extraordinary how all these wide range of sensors. Some of them exist, some of them don't exist, some of them are at the cutting edge and are just beginning to exist, are making a big difference. You did ask about sonar, and I do want to make a comment about that. So back in the day, there was no LiDAR. So when I was, in fact, a graduate student, we didn't have LiDAR. And we spent so much time trying to get robots to work using sonar. And that was a problem because sonar has a very small cone of reliability. So if you're within plus minus 7.5 degrees of the normal to the surface you're trying to measure, you get you hear the reflection back. If you're further away, your sonar beam will just bounce all over the place and you'll get the wrong answer. And so interestingly, we spent so much time and energy getting our sonar to be exactly normal to what we were trying to measure, and nothing worked. I mean, it worked some of the times, but mostly things didn't work. Then the LiDAR was introduced, and all of a sudden, all these algorithms that didn't work, all of a sudden they started working because light is a much more reliable sensor than sonar. And so the advantage of a wide range of sensing modalities is that you can pick the right sensor for the right task.
All right. Well, thank you so much, Danielle. That was absolutely amazing. Appreciate it.
Thanks for coming.
Thank you. And so we're going to have our next speaker is coming on April 21st. It's Alvin Grayland, who's going to be talking about the realities of the U.S.-China AI arms race. So we'll see you in a couple of weeks. Bye.